Now let's take a look at the component testing and repair. There are many types of electronic components, and a small set of parts constitutes the core of most electronic products. These are fuses, resistors and potentiometers, capacitors, inductors and transformers, diodes and rectifiers, transistors, relays, and voltage regulators. Now let's look at the most common components and how to recognize and test them. In the upcoming lectures, we will cover out-of-circuit testing, the kind you perform after removing the part from the board. Once you have found a component you want to test, or one that is obviously blown, you need to remove it from the board. In a single or double-sided circuit board, removal is easy. A little solder wick or a solder sucker will clear the joint. After that, all you need to do is pull the component out. Unless both sides of the board are accessible, you will have to remove the board from the unit before you can desolder anything. Either way, first make sure power is disconnected and all capacitors are discharged before desoldering anything. Now, anytime you need a new part, the best case scenario will be to buy an exact part with the same part number, but that is usually not possible for all parts. In most cases, we have a few options. The first is, if you have stockpiled components like these, see what you have, which is a close enough match. Also, when using parts that have been sitting around for a long time, take some sandpaper or a blade and scrape off the oxidation that might have built up on the component leads. Otherwise, soldering these leads will be unsuccessful. Here we have some oxidation on the leads. To remove it, we can simply use a blade like this one to scrape it off before soldering. Or we can also use a sandpaper for this. Now, substituting a part with something close but not an exact match requires consideration of how the part is being used, what parameters are critical, and what you can get away with a particular application. The general idea is that a part with better specifications can substitute for a lesser one, but not the other way around. Fuses protect circuitry and prevents fire hazards by stopping the current when it exceeds the fuse's rating. Though simple in concept, fuses have surprising number of parameters, including current required to blow, maximum safe voltage, maximum safe current to block, and speed of operation. The primary parameter is the current required to melt the fuse. If you are not sure of anything else, be sure to get that right when replacing a fuse. The speed at which fuse acts is also important in some devices. Time delay or slow blow fuses are used for applications like motors, which may require momentary high startup currents. Ultra-fast acting fuses are used with specially sensitive circuitry that must be protected from even transient overcurrent conditions. Most consumer electronic gear uses standard fuses. which are considered fast acting but not ultra fast. Also, fuses come in many shapes and sizes. You will find fuses in holders and also soldered directly to the circuit board. Like these are removable fuses, these are cartridge fuses. We have the rating written on the end caps. This is 0.5 ampere 250-volt fuse. We have them in different sizes too. This is a 13 ampere. We have device mounted fuses like these, which can be replaced by unscrewing and changing the fuse inside. We also have this type of PCB holders. And we also have fuses which are directly soldered on the PCB. Now, most things that plug into the wall will have a fuse on the live side of the AC line, usually right as it enters the device, before it even gets to the power switch. Battery operated gadgets often have fuses too, typically between the battery's positive terminal and rest of the unit. Some products will have multiple internal fuses protecting various parts of the circuitry. Now let's look at the common failure reasons of a fuse. A short circuit pulls too much current through the fuse, so it blows. Sometimes you may run across a fuse which has fatigued with age and use, finally failing. If it is a glass fuse like this, take a look at the insides. When the two wires are almost touching and there is no discoloration, the fuse blew gently, and there is a possibility that the circuitry isn't shorted. The fuse wire just gets warm enough to fracture, but there is no malfunction in the circuitry. If you see a white gap between the wires and black spots inside of the glass, like this case, the fuse blew hard, indicating a lot of current and certain circuit failure. Very rarely, fuses can develop resistance, continuing to pass current but interfering with the full flow. Now let's check how to test the fuses. Checking fuses with your multimeter's ohm scale, it should read 0 ohms. If you see 1 or 2 ohms, try touching the meter's leads together. You may get the same reading due to the resistance of the leads themselves. If not, the resistance is definitely in the fuse. Replace it. A blown fuse will read completely open. We see there is 0.5 ohms of resistance, and if I directly touch the leads together, we see 0.4 ohms of resistance. That is due to these leads going into the multimeter. And let's take a look at a blown open fuse. Now, how to repair the fuses? You should replace fuses with the exact type or some lower value. For example, you can replace a 12 ampere fuse with a 10 ampere fuse of the same type. You should never exceed the rating of the fuse that was originally in the device itself. Now let's take a look at how a fuse blows. I will create a short circuit condition for the fuse and make it blow gently. Now it is currently set to half an amp. Now this fuse is rated for half an ampere, so it will be fine with half an amp. But what happens if I start increasing the current? Now let's take a look at resistors and potentiometers. Resistors offer opposition to current, dissipating the opposed power as heat. The opposition limits how much current can flow, as described by Ohm's law. Limiting current is a vital function in any circuit, so every electronic product has resistors. They come in many shapes and sizes, but those with leads are easily identifiable by their color bands. Some large resistors are marked numerically, as are some of the surface mount parts. Like this resistor here, this is 200 ohms. The basic type of resistor found in virtually everything is the carbon resistor. Made from a carbon compound, these resistors run the full ranges of values from less than 1 ohm to 10 mega ohms or more. The tolerance for standard carbon composition resistor is plus minus 5%. That is, the measured value should be no more than 5% higher or lower than the stated resistance. In addition to the resistance value, the power dissipating capability of a resistor, measured in watts, is an important factor. Since power is dissipated as heat, knowing how much heat the product can take before disintegrating is vital. Standard carbon resistors are rated at a quarter watt, with some highly larger ones able to dissipate half a watt. A potentiometer is a variable resistor. They have three connections. The outer two are connected to the substrate on which the resistive element is formed, with one lead at each end of the resistor. The center lead goes to a wiper, a movable metal contact whose point touches the resistive element, selecting the resistance value that rises relative to one lead while falling relative to the other as you turn the knob. Potentiometers are used to adjust operating parameters for analog signal and power supply voltages. Here we have potentiometers in different sizes. Usually the value is written on them. This is 50K. This is 10K. This here is an older style, bigger potentiometer. This is 7 ohms, 100 watts. The mechanism you can see clearly here. We have the full resistance between pins 1 and 3, and the pin number 2 is connected to a movable wiper. As you turn the potentiometer, this changes the position and changes the relative resistance between these pins. Now let's take a look at the common failure reasons of resistors or potentiometers. Resistors rarely fail on their own. Heat caused by passing too much current burns them out. Carbon resistors can catch fire and become charred when a short circuit in some other part pulls a lot of current through them. Most failures in potentiometers are caused by wear or dirt where the wiper makes contact with the resistive element. The symptom is an inability to set the pot to specific spots without the wiper losing contact with the element. Now let's take a look how to test resistances and potentiometers. Using a multimeter ohm scale to see if the resistance is within the specified tolerance range. Most resistors do better than their tolerance, but expect a small difference between what's on the code and what you measure. Here we have 215 ohms. For potentiometers, test the outer two leads on a 3-leaded potentiometer with your multimeter's ohm scale. It should read something close to the printed value. Like in this case, we have a 10 kilo ohm potentiometers. If I attach the multimeter on the outer two leads, it is 9.57 kilo ohms. Now to check for integrity of the wiper's contact, connect the meter between one end of the potentiometer and the wiper. Slowly turn the pots to its range, observing the change in resistance. There should be no jumps there. If I connect one lead to the middle wiper, we can see it is 6.08. And as I move it in this direction, the resistance increases, and in the other direction, it drops. Same for this bigger potentiometer. This here has a faulty wiper because you see the resistance value keeps changing. But if you check the resistance between the two terminals, we see 7.3 ohms, which is the rated value of this. Now let's see how to repair these. The most common resistors are carbon composition types and they are easy to replace. What matters most are the resistance value and the power dissipation capability. It's fine to use a 1% precision resistor in place of a standard 5% one. And it doesn't hurt if the replacement is rated to handle more power, as long as it fits in the required space. If the original resistor was a special type, such as a wire wound or low noise metal film resistor, it is important to replace it with the same type. Those kinds of resistor are used only in special applications. You won't find them very often in consumer electronic gear, but they show up now and then in switching power supplies, preamplifiers, and stage handling, particularly small signals like receiver front ends. If you can't find the exact value you need, consider the original part's tolerance and try to combine a few other resistors to get a value well within the original part spec. For instance, if you need a 3.3 kilo ohm resistor, you can put a 2.2 kilo ohm and a 1 kilo ohm resistor in series. Resistor values in series add together so that you will get up to 3.2 kilo ohms. If the original resistor had a 5% tolerance, as most do, it could vary by plus minus 165 ohms and still be okay. So 3.2 kilo ohm would be fine as long as the combined resistor's own tolerance didn't push the total value outside the tolerance range of the original part. Check the real value of the combination with your multimeter to be sure. The opposite is true for resistors in parallel. The resistance value goes down. Two resistors of the same value will produce half the resistance. Now let's see how a resistor fails. I'll be using this 200 ohm resistor. Let's start with 12.5 volts and let me change the current limit to a lower value. So we can see the resistor is dissipating 0.6 watts of power. That is near its limit, which is half a watt. Now if I increase the voltage, you can see it is dissipating much more power. And now the resistance has went open circuit. Now let's take a look at capacitors. Capacitors are basically two plates separated by an insulator or dielectric layer. A charge builds up on the plates when the voltage is applied, which can then be discharged back into the circuit. Capacitors come in many types, including ceramic, electrolytic, tantalum, and plastic. Different types of capacitors cover various ranges and are used for different purposes. Here are some common ones. The first one we have is the ceramic capacitors. These cover very small values from a few picofarads up to zero point 0.1 microfarad and are used in resonant radio circuits and bypass application. The next is plastic film capacitors. These start at around 0.001 microfarad or 1000 picofarad and may go as high as 0.47 microfarad. These are used for bypass and coupling and are sometimes found in time constants because of their excellent stability over wide ranges of temperatures. The next is tantalum capacitors. These range from 0.1 microfarad to around 47 microfarad and are a special type of electrolytic capacitors with lower impedance at higher frequencies. These are used in filtering and bypass application when high frequencies are present. Last but not the least, we have the electrolytic capacitors. These start at around 0.47 microfarad and cover the highest ranges, on up to tens of thousands of microfarad. They are used for coupling and filtering. Now let's take a look at the common failure reasons of capacitors. Different styles of capacitors fail for different reasons, depending on how they are used and to what condition they are subjected. Generally, an application of voltage above the capacitor's rating can puncture the dielectric layer. Heat can dry or crack them, and some wear out with age. Ceramic and plastic capacitors very rarely fail. If these capacitors appear unharmed, they are almost certainly okay. Electrolytic capacitors are the most failure-prone components of all. Part of their charge storing layer is a liquid electrolyte, and it can dry out, short out, swell, and even burst the capacitor seal and leak out. Heat, voltage, and age all contribute to their demise. The constant charging and discharging as the smooth ripple currents in normal operation gradually wears the capacitors out. We usually have the maximum temperature rating, the capacitance, and the voltage written on the capacitors itself. In case of excess pressure, we have these vents which let the hot exhaust gases out. The commonly used switching power supplies with their fast pulse action has accelerated electrolytic capacitor failure, and application of even a little reverse polarity current will trash electrolytics in no time. A leaky rectifier will permit some AC to hit the filter capacitors connected to it, resulting in ruined caps. If you replace them without changing the rectifier, the new parts will fail very quickly. Failure modes include shorts, opens, loss of capacitance from age or drawing out, electrical leakage, which is essentially a partial short, and increased internal resistance, or ESR, which stands for equivalent series resistance. If you see a bulge in the top of the capacitor, or anywhere on it for that matter, it is a bad capacitor and must be replaced. Keep in mind that a capacitor can also exhibit high ESR or decrease capacitance with no physical signs. Sometimes the stop portion will be bulging out, and sometimes there will be leakage at the bottom of the legs. That is a clear obvious sign of capacitor failure. Tantalum capacitors use a solid electrolyte in the dielectric layer, which is quite thin. Consequently, they are prone to shorts from even momentary voltage spikes exceeding their voltage rating and punching holes in the layer. And they are even less tolerant of the reverse current than the standard electrolytics. Tantalum capacitors short more often than they wear out. Now let's see how to test the capacitors. Firstly, to test a capacitor, you need to remove it from the circuit, either both of the legs or only one of the leg. And after that, make sure the capacitor is discharged. And then you can use the capacitance measurement function on your multimeter, or if you have an ESR meter, you can use that too. If you don't have the ESR meter or the capacitance measurement function on the multimeter, you can use the ohm scale on the multimeter to check for shorts. Small value capacitors will appear open on a multimeter because they charge up too quickly for you to see the resistance rising. For electrolytics over 1 microfarad, you can observe the resistance rising. Make sure the capacitor is discharged before you try to test it. With a polarized capacitor, connect the test lead positive to positive and negative to negative. Most polarized capacitor will survive a reverse test, but tantalum capacitors may not. Even momentary reversed voltage can short them out. So let's see how to measure the capacitance. If you have a capacitance measurement function, that's very easy. You just need to connect the capacitor to the correct polarity with the multimeter. Positive to positive, negative to negative. And we have the value 0.94 megafarad or 940 microfarads. And the rating is pretty close to it, 1000 microfarads. Let's check this high voltage electrolytic. Here we have 56 microfarads. So this capacitor is faulty. It should be around 120 microfarads, but it is only 56 microfarads. Now, if your multimeter doesn't have this capacitance measurement function, we can use the resistance measurement. You can put it in the lowest measurement. I am currently putting it in the 200 ohm range. Firstly, discharge the capacitor. And notice the resistance rising as soon as I connect it. I'll put it in an even higher range now, 20 kilo ohms. Now the best way is to use an ESR meter. A budget one like this will also suffice. To use these, we simply connect the capacitor to the test leads. Firstly, we will make sure the capacitor is discharged. I am shorting the pins together. Now we can see we have some additional parameters like 945 microfarads, equivalent series resistance 1.9 ohm, voltage loss 1.1%. Firstly, discharge it. Here we see the capacitance is still low and the ESR is high. So this is an example of a faulty capacitor. If you see a high ESR like this, then this needs to go. Also, the capacitance is pretty low. Instead of 120, it is around 50 microfarads. Now let's check how a good capacitor should look like. This is a fresh capacitor. This should be around 2200 microfarads. Here we see 2128 microfarads and ESR 1.8 ohms. So it is pretty close to its rated value. This is a 10 microfarad 450 volt capacitor. As we can see, the capacitance is alright, but the ESR is very high, which is 6.2 ohms. Now let's see how to repair capacitors. Most of the capacitors you will replace will be electrolytic ones. The major factors in an electrolytic are its size, its capacitance, its voltage rating, and its temperature rating. Also, switching power supplies and computer motherboards often require capacitors with specially low ESR to smooth out the fast, sharp pulses those circuits produce. Replacing such parts with standard electrolytics will cause malfunction. Here we see the maximum voltage this capacitor can withstand, the capacitance, and the temperature rating. The most important consideration is the size. It has to fit on the motherboard in the allotted space. Next is the voltage rating. Electrolytics will not withstand voltages higher than their rating. Their life is reduced even by running them at voltages under but close to their ratings. A usual rule of thumb is if you have an application with, let's say, 12 or 15 volts, you should use double that, or whichever capacitor value is the closest to it. To rectify 12 volts, you can use 25 volt capacitor. The capacitance rating is not as critical. Most electrolytics have wide tolerances in the range of -20 to +80%. If the capacitor is being used to couple signals from one stage to another, the capacitance value is more important than it is when the part is a bypass or filtering capacitor. You might find a few electrolytic coupling capacitors in audio and video gear. In audio amplifier stages that use capacitors of a few microfarads from an emitter to ground, it pays to keep the value close to the original because a higher value might increase low frequency response, upsetting the audio quality. You will see many electrolytics in power supplies for bypassing and filtering. From simple analog devices to today's most complex gear, those are the parts that usually need replacement. If your available replacement value is less than 150% of the original value, you can go ahead and use it. Combining capacitors to get near the value is fine in most applications. I do not recommend it though for the big storage capacitors at the input of a switching power supply or in other high voltage circuits. Putting capacitors in parallel adds their values and putting them in series drops the final value. Capacitors combine exactly opposite to how resistors do. When putting polarized capacitors in series, make sure they are connected positive to negative so that you wind up with one positive at one end and one negative at the ends of the string. When you parallel them, connect all the positive terminals to each other and the negative terminals to each other. In either case, be sure each capacitor's voltage rating is equal to the entire applied voltage. When in series, the individual capacitors won't be subjected to the full voltage during normal operation, but a big voltage spike can occur when the power is first applied. So it is a smart safety move to be certain every one of them can handle it. Especially in power supply applications, the capacitor's temperature rating matters. Electrolytics that get charged and discharged very fast, as they do in a switcher, can become warm from the power dissipation of their internal resistance. Standard electrolytics are rated to operate at 85 degrees Celsius, rated as high as 150 degrees Celsius. Follow the temperature rating of the original parts if you want the repair to last. The higher temperature capacitors are more expensive component and there is a reason for them being there. For quick testing purposes while troubleshooting, you can disregard the rating because the part won't be in use long enough to fail from overheating. But in long term, you should replace the capacitor with the exact temperature rating or higher. Tantalum capacitors should always be replaced with the same type. They have lower impedance at high frequencies than the standard electrolytics and are only used where those matter. Replacing a tantalum with an electrolytic will result in performance degradation or circuit failure. The capacitance tolerance of tantalum is much tighter than that of standard electrolytics. So use a capacitor with the same value and increased voltage rating is fine. Now let's take a look at inductors and transformers. Inductors or coils generate a magnetic field when a current passes through them. When the current through the inductor stops or changes direction, the field collapses and creates a current in the wire opposing the change. The effect is to store some of the energy and put it back into the circuit. Two inductors wound on the same iron core can be used to convert one voltage and current to another by creating a magnetic field in one coil and using it to generate a current in the other coil, which may have different number of turns of wire, thus creating a different voltage. This arrangement is called a transformer. Inductors and transformers are used to convert voltages, to couple signals from one stage to another, and to filter or smooth voltage variations. They can also be found in power supplies, either switching or linear. Now let's take a look at the common failure reasons of inductors and transformers. The windings in inductors or power transformers sometimes open when too much current overheats them and melts the wire. Now let's see how to test an inductor or a transformer. You can use your multimeter to test for continuity from one end of the coil or section of a transformer to its other end. You can also use the ohm scale to check for shorts from winding to the core and between unconnected windings. It is very hard to tell whether the windings are shorted to each other in the same coil using the ohm scale on the multimeter. The difference can be so slight that it is undetectable. You can use a LCR meter and know the correct inductance. That will give you some idea. Here we have 16 kilo ohm in this primary coil. And if we take this inductor, we have 0.6 ohms, out of which 0.5 is due to the wires in these probes. So that inductor is only 0.1 ohms. This is around 0.65 ohms. Now let's see how to repair the inductors. Inductors should be replaced with an exact matching part with the same inductance and current ratings. The transformers can be replaced with the exact same one or something with a higher VA rating, as long as it fits in the original place. Diodes are one-way valves. Current can flow from the cathode, the negative side, to their anodes, the positive side, but not the other way. They are made from silicon doped with materials that cause the one-way current flow with two dissimilar slabs touching at a junction point. Large diodes used in power supplies are called rectifiers, but they do the same thing. Two of them in one package sharing a common terminal are called a double diode or a double rectifier. Four of them arranged in a diamond-like configuration are called bridge rectifier. Bridge rectifiers may be marked with their part number or none at all. Usually you will see the AC sign and the positive and the negative. In this we see the middle two leads are the AC inputs and these are the positive and the negative. Single diodes and rectifiers have a band at one end indicating the cathode. They are marked with the number, which does not indicate their operating parameters like maximum forward and reverse operating voltages and maximum current. To get those, you must look up the part number online. Diodes and rectifiers are common parts in pretty much every electronic product. Rectifiers convert the incoming AC power to DC power. They convert the pulses in a switching power supplies back to DC as well. Bridge rectifiers are commonly used to change AC waveform to the appropriate positive and the negative output terminal. That is called a full wave rectification. In half wave rectification, the reverse polarity side of the waveform is simply blocked with one rectifier. Now let's take a look at the common failure reasons of diodes. Diodes and rectifiers can fail from applied voltage that exceeds their limits. But the most common cause is too much current and the heat they produce. Often, a short circuit elsewhere in the circuit has pulled excessive current through them. Sometimes they just fail with age too. Failure modes include opens, shorts, and leakages, with opens being the most common. Now let's see how to test a diode. Multimeters include a diode test function that shows the voltage drop across the part, indicating whether it is passing current. To be sure, test the diode in both directions. A standard silicon diode or rectifier should show a drop of 0.6 to 0.8 volts in one direction and appear open in the other. Here we have 0.634 volts of drop. Here we have 0.552 volts of drop. And in the other direction, we see an open circuit. Now, even a small voltage drop in the reverse direction suggests a leaky diode that should be replaced. Diodes with excessive voltage drop in the forward direction should be replaced as well. To test a bridge rectifier, put your meter's black lead to the positive of the bridge, like this. Now test it while placing the red on the AC sides. You will see a drop like this, 0.55, and in the other diode, 0.55. Now place the positive on the negative of the diode and once again check it, 0.545, and in the other 0.551. So this bridge rectifier is alright. Now let's see how a simple diode fails. I will simulate an overcurrent situation on a diode. Let's start with 1 ampere of current. 1 ampere is what this diode is rated for, and increase it bit by bit. Now this diode failed open circuit. We can see no current is flowing through it. Now we have two diodes which have failed in a different way. The first one here failed open circuit, and the second one here, this has failed short circuit. So now let's take a look at the characteristics now. We can see we still have 0.6 volts of voltage drop. And in the other direction, we have 2.8 volts. So this is definitely faulty. And the one which failed short circuit, this has 2.8 volts of voltage drop in one direction. And same for the other one. It fell apart on its own. Now let's see how to repair a blown diode. Diodes and rectifiers have four primary characteristics: forward voltage, reverse voltage, current, and speed. The forward voltage specification tells you how much voltage can be across the part in its conducting direction. You will not see this specified because in an AC circuit, the forward and the reverse voltages is usually the same. The reverse voltage is specified as peak inverse voltage or PIV and tells you how much voltage the diode can withstand in its non-conducting direction. Exceeding the PIV and the part will arc over inside and be destroyed. The current rating indicates how much current can pass in the conducting direction without overheating the part and burning it out. No current should flow in the reverse direction, of course. The speed of a diode is very important in some small signal applications like radio, signal detection. It is also critical on the low voltage side of a switching power supply, where the part will be rectifying the fast pulses from the conversion transformer. In the sections of power supplies operating at the low frequency of the AC line, any rectifier is more than fast enough. The bridge or individual rectifiers at the AC side of the cord are not high-speed devices, nor the rectifiers on the low voltage side of a linear supply. These kinds of rectifiers can be used to rectify the incoming AC into DC, and the frequency is 50 or 60 Hz. When replacing a normal low-speed rectifier or bridge rectifier, pay attention to the peak inverse voltage and the current rating. As long as those are equal to or higher than the original part's rating, the new part should work fine. Search for high speed or fast recovery rectifiers in a substitution chart online. Replace them with parts of equal or better peak inverse voltage, current, and speed. Never replace a high speed rectifier with a low speed part, even if the peak inverse voltage and the current specifications are fine. It will not work. There are some other special purpose diodes too, including germanium diodes. They are glass covered but noticeably larger than normal silicon diodes. Gallium arsenide diodes, tunnel diodes, and varactors. They are found in receivers, front ends, and other weak signal exotic applications. You will not find them very often, but they must be replaced with the diodes of the exact same type. In this lecture, we will take a look at the transistors. Transistors are the active element that do most of the work in the circuits, amplifying, processing, and generating signals, to switching currents and providing the power needed to drive speakers, headphones, motors, lamps, and many other devices. Transistors act like a potentiometer, but instead of a hand turning the knob, a signal does. There are thousands of subtypes of transistors, but most fall into three categories: bipolar, junction field effect transistor or JFET, and metal oxide semiconductor field effect transistor or MOSFET. Now let's take a look at them one by one. The first one is the bipolar transistor. These are the standard type used in products since the 1950s. They come in two polarities, NPN and PNP, and consist of three elements joined by two junctions. These three elements are the base, emitter, and collector, each with its own lead. Current passing between the base and the emitter permits a much larger current to pass between collector and the emitter, with one of them being fed from the power supply. In most configuration, the signal is applied to the base, causing a bigger version of the signal to be formed from the flow between the collector and the emitter. The ratio of base to emitter current to collector to emitter current is the transistor's current gain and is the inherent ability of the transistor. In an NPN transistor, the base must be positive with respect to the emitter for collector to emitter current to pass. In a PNP transistor, the base must be negative, so the two types are of opposite polarity and cannot be interchanged. Most transistors used today are NPN, but you will find circuits with some PNP parts. Here we have a small signal NPN transistor. These are the three leads. If you apply them on a transistor tester, we have an NPN transistor. We have an NPN transistor with emitter base collector configuration. So this is emitter base collector. The current gain is 429 times. The forward voltage is 678 millivolts. This is also an NPN transistor, but in a different package. This is a power transistor, 3055. Now let's take a look at the JFETs. They work on a similar principle. They label their three elements differently. Instead of the base controlling a terminal, it's called the gate. The emitter is called the source, and the collector is the drain. Instead of current passing from gate to source, application of a voltage to the gate goes nowhere but results in an electric field that controls the channel in the transistor, permitting current to pass between drain and source. This gives the JFET a very high input impedance, which is another way of saying that it does not take much signal to turn it on. Next, we have MOSFETs. They are similar to JFETs and they use the same terminal names, but their internal construction is a bit different. They have even higher input impedance and some other desirable characteristics that have resulted in them pretty much dominating the FET applications. You are much more likely to see nothing but MOSFETs in newer equipments. Like bipolars, FETs come in two polarities, P channel and N channel, corresponding to PNP and NPN bipolar transistors. They also come in enhancement mode and depletion mode types, specifying what happens when the gate voltage is 0. An enhancement mode FET will turn on with no voltage at the gate. Like a bipolar transistor, it requires a bias voltage to turn on. A depletion mode FET will turn on with a 0 gate voltage. The only way to turn it off is to apply a voltage of the opposite polarity to the one that will increase current flow. Knowing the basics of how these parts work is essential for understanding how to troubleshoot circuits using them, which are pretty much all of the circuits made since the 1990s. Here we have a MOSFET, IRL Z44N. This is a logic level MOSFET, so it is pretty common to be used with microcontrollers which work with 5 volt. As you can see, transistors have many parameters, so it is not surprising that there are thousands of subtypes with different gains, power dissipation capabilities, frequency limits, and so on. Some are similar enough that they can be interchanged in many circuits, but most are not. To replace one part number with another, you need a transistor substitution cross-reference guide. Now let's take a look at the common failure causes. Transistors are not specially fragile, but they work hard in many circuits and fail more often than they do most components. Overheating due to excessive currents will burn them out, as will a high voltage. Generally, circuits are designed to avoid applying voltages above their transistor's rating, but it can happen due to a fault, especially in power supplies. MOSFETs are particularly prone to shorts from static electricity. Sometimes the internal structure of a transistor develops a tiny flaw, and the thing self-destruct with no apparent cause. In fact, many random product failures occurs for precisely this reason. You change the part and the unit works again, and you never find any reason for the dead transistor. Now let's check how to test the transistors. The best way is to use a transistor tester like this one. If you do not have one, you can use your multimeter's diode test function, or even lacking that, the ohm scales to check for short. If you get near 0 ohms between any two leads, check in the other direction. If it is still 0, the part is definitely shorted. Checking for opens is a bit more complicated because some combination of terminals should look open depending on to what the control terminal is connected to. Connecting the base of a bipolar transistor to its collector should result it in turning on, showing measurable resistance between the emitter and collector in one direction. Connecting the base to the emitter should turn it off. Now for MOSFETs, we have a quick way to check. The type used as chopper in switching power supplies and output stages and in some other applications. Most of the power MOSFETs you will encounter will be N-channel and their pinout left to right is usually gate, drain, source. Now to check them, firstly, place your multimeter in the diode check function. Now let's see how to check a MOSFET with only a multimeter. We have a IRL Z44N here. So the first step is to touch all 3 pins together to discharge the gate. Now place your positive probe on the drain and the negative probe on the source. We have gate, drain, source. So positive on drain and negative on source. We can see the diode is not conducting at all. Now to charge the gate, we need to charge it with a higher voltage with respect to the drain. So I'll keep the negative probe on the drain and the positive on the gate for a second. And now when we move back, we can see there is a 0 volt voltage drop in the MOSFET. And if I touch the gate, we can see the resistance is rising. So once again, open circuit, charging the gate. Now 0 resistance in the MOSFET. And touching the gate, the resistance starts rising again. The best way to check power MOSFET is by using the component tester. But if you do not have the component tester, you can use a simple multimeter like this one too, set to a diode test function. And now with the transistor tester, it is much more simpler. You just need to connect the leads. You just need to connect them like this. And here we have N-type enhancement mode MOSFET. Gate capacitance 1.63 nanofarad, threshold voltage 2.1 volts, and pin number 1, 2, and 3, gate, drain, and source. And we have the forward voltage as 630 millivolts. To check the NPN transistors, we know that it is N, P, and N between these 3 leads. So if we again put our multimeter to the diode test and we put the first lead, the N type, to the negative, we will see a forward voltage drop of 680 millivolts. And again in the other direction, we can confirm it. So this is how we can check if a transistor is alright or not. And again, the best way is to use a component tester. Now let's see how to repair the transistors. Transistors are the most complicated part to substitute. Because many transistors have similar characteristics, a few hundred parts can be substituted for thousands of transistor types. You can search the part number online, but you will run into numbers for which you can't find a substitute, or there might not be a valid substitute. Even when a substitute component is available, you may prefer to speed up the repair process by using a part you already have. To choose your own substitute, it requires some understanding of the part's application and how a change in characteristics would affect the circuit performance. Some functions, like simple switching of a voltage to direct it to various circuit stages or turn an indicator on or off, will work with just about any transistor of the same basic construction, bipolar or field effect, and the polarity. Others, such as high frequency signal processing or current amplification in complementary output stages, often require stringent adherence to the original part specification. All this assumes you know the old parts number. Usually you will, but at times you might have to fly blind. If the original transistor literally blew apart, which happens occasionally when a lot of current has been pulled through one, there may not be a part number to read. Even when a number is visible, it could be a proprietary house number with no cross reference to a substitute. And some transistors, especially tiny surface mount ones, show no numbers in the first place. Sometimes the board will be marked with ECB or GDS, showing what terminal goes to which pad. ECB indicates emitter, collector, and base, and thus a bipolar transistor. GDS means gate, drain, and source, the terminals of a field effect transistor. Those markings also give you a strong clues to the part's polarity. If C goes to the positive side of the things, it is an NPN. If E does, it is an PNP. With a FET, if D is positive, it is a N-channel part. If the S is positive, it is a P-channel part. Usually, some FETs are symmetrical and can be used either way. Without board markings or a part number, the transistor is a total mystery. You can use your scope and understanding of basic transistor operation to deduce the part's polarity and layout of connections. Start by looking for the power supply voltage feeding it. If it is positive and fed through a resistor or a transformer, you have probably found the collector of NPN transistor or the drain of N-channel FET. Find the stage input by looking for whatever signal operates a transistor. If it is a continuous signal, you should see it. If it is something that happens only when you press a switch or some other operation signal of that circuit, create those conditions and find the signal. When you find it, you have found the base or the gate. Whatever's left will be emitter or source. Most bipolar transistors are NPN. If the connection to the positive supply line is direct, without a resistor, or there is a resistor but it is of very low value, the transistor could be PNP, and that connection would be the emitter. Find what looks like the base by scoping for signals. See if there is a resistor from the base to the transistor's terminal closest to the supply. PNPs are used to turn on and pass the current from the supply to some other circuit when the input signal goes low. The resistor going up towards the supply keeps the base high and the transistor turned off until the input signal pulls it low. You will find PNP circuits of this sort in power switching sections of battery operated products. Assume the part is an NPN bipolar transistor and you will be right most of the time. If your replacement turns out to be the wrong polarity, the circuit won't work. But trying it should not do any damage. If the transistor is a part of complementary push-pull amplifier, the configuration uses NPN and PNP in a more complicated, hard to deduce ways. And if the original part was a FET, the issue of enhancement and depletion modes and JFETs versus MOSFET makes the whole thing very tough. Getting the identification correct requires your understanding how these parts work and looking at the bias on the gate terminal to infer what the output should do as the input changes. Don't try to substitute chopper transistors in switching power supplies without knowing the correct part number and finding a legitimate substitute from a cross-reference. Most choppers are power MOSFET with specification that must be closely matched for reliable operation. Even if a close substitute works, it will not run for long before failing. Sometimes even a very close substitute will die quickly, and only the part that will work is an exact replacement of the original part number. In some cases, the original and replacement transistors are electrically compatible, but the arrangement of leads, called pin basing, is different. Most small signal American transistors are EBC, left to right, while Japanese parts are usually ECB. You can replace one layout with the other as long as you switch the two leads, being careful not to let them touch as they rise from the boards towards the transistors. Small FETs are usually SGD. Power transistors are usually BCE with C connected to the metal tab if there is one. But always check to make sure. Power FETs typically use GDS with D connected to the tab. Once you have figured out what should go where, whether from the original part or the scoping and deducing, you can proceed with trying out the new part. The primary characteristics to be concerned with are gain, high frequency cutoff point, and with larger parts, power dissipation capability. Secondary characteristics, but still very important, are the maximum voltage permitted from base to the emitter and from the collector to emitter. Very often you will find a transistor that's pretty close but has a little more or less gain. Depending on the application, the part might still work. If the circuit is linear, producing output proportional to the input, the transistor isn't normally saturated or fully turned on, so a slight gain difference may not cause a problem. In switching circuits like backlight inverters, inadequate gain can result in lots of heat from the transistors not fully turned on, burning out the part in a hurry. Too much gain in a linear circuit may cause distortion or increased output. Not enough usually just results in a bit less output. The high frequency cutoff point specifies at what frequency the transistor's gain will have decreased to 1. In other words, it won't be amplifying at or above that frequency. In low frequency applications such as radio, any transistor will more than fast enough. At radio frequencies, the situation can be quite different, requiring a transistor whose cutoff frequency is approximately equal to the original part specifications. Too little might result in low or no output, while too much could result in unwanted harmonics riding on the desired one. When in doubt, go for too much as long as the difference isn't excessive. At least the thing will try to work. Power dissipation is also very important. The new part should be able to dissipate at least as much power as the old one. A better dissipation spec is fine. Rarely, this is an issue with small signal transistors. Maximum permissible inter-electrode voltage must be respected. Exceed them and the transistor might blow out. Most transistors' collector to emitter specs are well beyond what a small signal circuit produces. The circuit's base to emitter voltage, however, could exceed the capability of some replacement parts, so keep an eye on that. Large parts used in output stages can have pretty high voltages applied from collector to emitter, so don't take that spec for granted. If all this seems overwhelming, stick to the replacement part numbers from a cross-reference online source and you will be fine. Even with expertise, matching up transistors is a very tricky process and requires experience. Now let's take a look at voltage regulators. Voltage regulators take incoming DC and hold their output voltage to a specific value as the incoming voltage fluctuates or the load varies with circuit operation. They are of two types, linear and switching. Linear regulators acts like automatic variable resistors passing the incoming current through a transistor called the series pass transistor and setting the base current to keep the output voltage constant. When the load changes and the voltage increases or decreases, the regulator detects and adjusts the base current to compensate, altering the transistor's resistance and permitting more or less current to go through it. The power lost in the resistance of the transistor is wasted and is dissipated as heat. Switching regulators chop the incoming current into fast pulses whose width can be varied. Those pulses are then applied to a capacitor which charges up, converting the pulses back to smooth DC. While more complicated, this approach supplies only the current required to keep the output voltage constant without wasting the excess as heat. So it is much more efficient. Here we have a linear regulator and this is a switching regulator. Voltage regulators are marked by part number like transistors. Some standard markings tells you that the voltage, which is handy. In particular, the widely used 7800 or 7900 series of linear regulators offer useful marking information. All regulators starting with 78 are positive regulators and 7805 is a 5 volt regulator while 7806 is a 6 volt regulator and so on. All parts starting with 79 are negative regulators. They use the same voltage numbering scheme. Other regulators don't necessarily indicate the voltage in the part number and you will have to look them up. Like here we have a 3.3. This is a variable resistor. Here we have 7805, which is a 5 volt regulator, and a 7806, which is a 6 volt regulator. These are 3.3 and 5 volts regulators, 3.3 and 5. This takes the incoming voltage from a barrel jack and converts it to 3.3 or 5. And this is a switching regulator, which has input and output, and the voltage can vary. So firstly, let's check what is the voltage that we are giving it. We are providing it with 11 volts, and it is regulating it down to 5 volts and 3.3 volts. Now let's take a look at the common failures. Pulling too much current through a regulator can overheat and destroy it. This is especially true with linear regulators. Voltage spikes can cause internal shorts, and random chip failures occur too. Switching regulators are prone to blowing their chopper transistors, just like switching power supplies. Now to test them, you can use the ohm scale on your multimeter to check for shorts. But that's about it. To evaluate a regulator properly, you need to be in a circuit receiving power. Now to repair them, they should be replaced with an exact matching part or something with a higher power rating but the same output voltage. Now let's take a look at relays. Relays are switches controlled by putting current into a coil, making them electromagnets. When the coil is energized, the resulting magnetic field pulls a metal plate towards it, pressing the attached switch contacts against opposing contacts. In this way, a small current can control a much larger one, just like a transistor does in switching mode. Relays may have any number of contacts for switching multiple unconnected circuits at the same time. As with switches, each set is called a pole. Also, some contacts might be normally open, meaning that they are not touching until the relay is energized, and some may be normally closed, which means the opposite. Each direction is called a throw. Thus, a double pole double throw relay would have two switches, each with three contacts: the normally open side, the movable contact, and the normally closed side. The maximum current the switch contacts can handle is shown. If the markings read 12 volt DC 3 ampere, that indicates a 12 volt coil intended to be driven with DC power, with switch contacts capable of switching 3 amps. Relays are widely used to switch large currents with smaller ones, and they make an audible click when they switch. Right here we have a 5 volt relay which can switch 10 amperes at 250 volts AC, or 15 amperes at 125 volt AC, or 10 ampere at 250 volt AC. Here we have the same relay but in a module. We can also have many relays in a single module. Now let's take a look at the underside of the relay. Here we have 5 contacts. These two are used to power the coil, and these are the contacts of the switch. One on this side is the normally closed contact, and this one is normally open contact. Now let's check the common failure causes of relays. Relay troubles usually involves the switching contacts, the corrosion from age and oxidation, as well as pitting from arcing when large currents are switched, cause resistances or flaky contacts. Sometimes the contacts will weld together, not wanting to open back up after the power is removed from the coil. This condition can be caused by arcing in the contacts, making them stick to each other, and by weakening of the spring which is used to pull the plate away from the iron core. Now let's take a look at a relay whose cover I have removed carefully. Here we see the main coil which acts as the electromagnet, and on the top we have the switch. When this electromagnet is energized, the switch comes down and closes the contact. Now let's see what happens when we energize this relay. Notice the moving contact on the top. Each time the power is applied to the electromagnet, the relay attracts the top portion. This is just 5 volts coming in from an AC adapter. Now let's check the same with another relay. Now I'll put the multimeter in continuity mode so that every time we touch it, it will beep. I will place one contact right here, and we can confirm this is the normally closed contact, because even when the coil is not energized, it is connected. And the other one, it is a normally open contact. So it will only connect when there is power applied to these magnetizing coil. So I'll apply power now. So to test the relay, use your multimeter's continuity or ohm scale. The coil should read 0 ohms. Check the normally closed contact with the meters. They should read 0 ohms or very close to it. And you can energize the coil using the same voltage that is written on the relay. This is a 5 volt relay, so I'm using 5 volts. Now when you energize the coil, as we have seen, the normally open contact gets closed. Initially the relay was like this. This contact was connected to this. When we applied power, it moved from here to here. On the module itself, we have the normally closed and the normally open contact marked. Now let's see how to repair a relay. Relays are failure prone, especially with age, and finding an exact replacement can be tough. When substituting relays, the most important specifications are the coil voltage and the current handling capacity of the contacts. Naturally, you need the relay to have the same numbers of poles and throws as well, so that it fits in the original place. The current required for the coil to pull in the relay also matters, but there is some leeway. Sometimes it won't be specified on the relay, but you might be able to find it from the part number by looking it up on the internet. You may see a resistance specified on the body of the relay. That's the coil's resistance, and you can calculate the current using Ohm's law. If the voltage is 12 volts, for instance, and the resistance is 500 ohms, the current that will pass through the coil is 12 divided by 500, or 0.024 amps. or 24 milliamps. As long as that's somewhere near the original part used, it should work fine. It's also okay to use a relay that takes any amount less current than the original. If the new one takes a lot more, it could overheat the transistors driving it. Relay coils pretty much always have diodes connected across them in reverse direction to prevent the reverse current spikes they generate from damaging the driving transistor. Sometimes the diode is inside the relay and sometimes it is on the board. Like in this case, we have the diode on the outside. This is the diode and this is the transistor which is driving the relay. In this case also, we have the diode on the outside and this is the transistor which is driving this relay. If the diode is inside, you can replace the relay with a diodeless version as long as you add a diode outside. Just about any silicon diode will do. If the diode is already outside and all you have is a relay with a diode, you can use it. You don't even have to remove the extra diode on the board. Just be certain that the coils connections are oriented so that the cathode of the diode connects to positive. Relay with diodes usually have plus and minus marked on their coil connections.